molecules, they act kind of like one piece. So they have a charge. So I gave you the list of them, and here's the list right here. So these are the 7.
And you want us to write it, right?
So these are the only 7. We went through all of them last time, but these are the only 7 that you've got to know. Even though, like, see that list? Like, there's a ton of them. There's a ton of them. The only ones you got to know are the ones that I have in boxes, and here they are written by themselves. Okay? So the hydroxide, when you see hydroxide in a name, you got to remember that that means it's an OH. Okay? Hydroxide, it's not a hydrogen and an oxygen. It's an OH, and it has a negative charge. So you want to remember, or like put on your note card, like put this definitely in your list, that if you see OH in the formula, then you know it's called the hydroxide. If you see NH4+, so notice how that's written, and I guess I didn't really think about this, but when you see NH4+, that means 1 nitrogen, 4 hydrogens, and together it has a positive charge. Okay? So the thing that's in the subscript is the number of atoms in the molecule, right? So like with NH4, 1 nitrogen, 4 hydrogens. That 4 is a subscript. But when you see stuff in a superscript, which means it's like up and above, then that's telling you the charge. Because I had some students that were like just trying to randomly switch them. And I was like, wait a minute. Where are you getting those numbers? And so I realized some people were actually thinking about it sort of backwards. So NH4+, if you see this, it's the only positive polyatomic ion. So it's always out front because remember your metals are positively charged and they're always written out front. So this is the only polyatomic that you'll ever see written first. All the other polyatomics that you've got to worry about are always written second. They're always going to be the negatively charged part of the ionic compound. Then we have nitrate, which is NO3. And so that negative right here, it's the charge on the NO3. So it's NO3 negative is a nitrate with 3 oxygens, and together it has a negative charge. Chlorate is ClO3, so it's a chlorine with 3 oxygens, and it has a negative charge. The carbonate is CO3, and it has a -2 charge. So you see it's written 2 negative, -2, same thing, okay? It just means that it has a negative, that's a double negative to it. A carbon with 3 oxygens. The sulfate is the sulfur with 4 oxygens, and it has a -2 charge. And then the one with the biggest charge is the phosphate. So phosphate is PO4, and it has a -3 charge. Okay, so we can just practice these that are listed here. So if you see NaOH, how would you name it? Use the whole name of the metal, but now you just use the name of the polyatomic. So it is hydroxide. Okay, now if you see NH4Cl, when you see NH4 out front, then remember that it's the ammonium chloride. If you see MgNO3 with the little parentheses, it's still just magnesium. What? NO3. Nitrate. Now, if you're given the name, like potassium chlorate, the big one is sometimes see potassium chlorate and think it's just a chlorine. So remember with that chlorate, when you see ATE at the end, then you know it's a polyatomic. The only 2 that don't have the ATE are the hydroxide and the ammonium. They're the oddballs of them. But most of them, if you see that ATE, remember that it's going to be a polyatomic, not just an ide. So potassium chlorate, in order to figure out this formula, you have to write the symbol. So what's the symbol for potassium? Okay, and what's its charge? How do I know the charge on the metal? What column is it in? So that means that it's a +1. Remember that the column is the charge for the metal. So that's how I know that this is potassium with a positive charge. I know the charge on the chlorate because it's listed. Okay? So if I'm given the name, write the symbol, assign the charges, and then if they're not the same, you have to do the swapping, just like what we did with the other ionic ones. These, do you see it's a 1 and 1? Do you see that I have a +1 and a -1? So the potassium and the chlorate are equal already by their charge, so it would just be KClO3.
You're not doing this side by side, are you?
No, I'm going down this one.
I'm saying you're going down the north.
Yeah, so looking at potassium chlorate, writing its formula, I have to first write the symbol, assign the charge, and if the charges are the same, then you know it's 1 and 1. But if the charges are not the same, I have to swap them. So lithium carbonate, what's lithium? Li, and what's its charge? +1, because it's in group 1, right? So it's in the first column, so it's a +1. Carbonate is CO3, and its charge is -2 or 2 negative, either one's fine. So now, see, they're not the same. Lithium's a +1, carbonate's a -2. So now I've got to swap them. So how many lithiums do I end up with? 2. So I end up with 2 lithiums. Remember, the charge on the carbonate tells me how many lithium, and the charge on the lithium tells me how many carbonate. So how many of those? Just 1. So if there's only 1, I just list it. That makes sense to everybody? So just think of these polyatomics. They really behave just like one thing. Okay? They behave like as if they're just a non-metal, even though it's a group of them, because together they all have a charge. So now, iron 3 sulfate. So what's iron? Fe. And the 3 tells me what? It tells me, the 3 tells me the iron is a +3. Remember, the Roman numeral tells me the charge. So Fe is a +3. And then sulfate. So sulfate is a SO4, and the charge is -2 or 2-. They're the same, doesn't matter. So you see they're not the same. So how many Fe's will I end up with? I end up with 2 Fe's. The charge on the sulfate tells me how many iron. But now, how many sulfates? They just swap. The numbers just swap. And I use parentheses. If there's more than one polyatomic, I have to put it in parentheses. Don't split it out. Don't worry about trying to split it out. So remember, if you have a polyatomic and there's more than one of them, don't try and like change the numbers of the formula. Just put it in parentheses and put that number outside. All right, so here's the last one. So the last one's ammonium phosphate, 2 polyatomics. So what is the ammonium? NH4, and it has a plus. And then the phosphate is with the -3 or 3-. That's either one's fine. So they're not the same. So how many NH4s do I end up with? 3. So this 3 on the charge on the PO4 tells me that I'm going to have 3 NH4s. So see, I just put a parentheses and I put the number. This doesn't look like a 4. I have to put parentheses around the NH4, put a 3 on the outside. What do I have to do with the phosphate? How many of those do I have? Just 1. So if there's just 1, I can just write it. Okay, I only have to use parentheses if there's more than one polyatomic ion. And that's the only time you've got to use parentheses. You only use parentheses with the polyatomic ions and only if there's more than one of them. So I'm going to give you a minute, see if you can do these. I'll go back, but everybody's got your worksheet. So remember on the little handout that I gave you last time, so this is this bottom one. And what I'm going to do is I'm going to go back so that you can actually use this to look at, because there's the polyatomics. Those are the 7. Those are the only 7 that I'll ask you. All right, let's see how you did. So the first one. So this is going from name to the formula. So sodium nitrate, what do I have to write down first? Na. And its charge? +1, right? And I know because it's in group 1. Remember, the metals are always positive by their group number. Okay? And then nitrate is NO3, and its charge is a -1. Do you see they're equal? So if they're equal, what does that mean? It's just the way it's written. I don't have to change anything. So it's just NaNO3. It's a 1-to-1 ratio, like sodium chloride, just 1 and 1. Calcium phosphate. Calcium is Ca, and its charge +2, because it's in the second column in the periodic table, so that tells you it's a +2. Phosphate is PO4 and has what charge? A -3 or a 3-, either one's fine. So they're not the same. Now I got to swap them. So how many calcium do I end up with? 3, because that's the charge on the phosphorus. Okay, so Ca3, how many phosphorus do I end up with? 2, right? Because calcium's 2. But remember, to say that, I've got to say the whole phosphate. So I have to use parentheses, and then I put the 2 outside. Lithium sulfate. So we got Li. And what's its charge? +1. And then sulfate is SO4, and its charge a -2 or 2-. So they're not the same. When I swap them, how many lithium? So I end up with Li2. How many sulfate? Just 1, because lithium's a +1. So it's just written as Li2SO4. I don't have to use parentheses for something like lithium. I only use parentheses if it goes around the polyatomic. So here's one that I've got a Roman numeral. So chromium 2 chlorate. So chromium 2 means what? It tells me the charge. Good. It tells me the charge on the chromium. So I know that the chromium's a +2. That's what the Roman numeral tells me. Ooh. Right? That Roman numeral 2 tells me it's a +2. Chlorate is Cl3, and its charge? A -1. So how many chromiums do I end up with? Nope. Just 1, right? Because it's the charge on the chlorate tells me how many chromium. So I've got 1 chromium. And how many chlorates, though? 2. Because the 2 from the chromium has to go after the chlorate. So it's parentheses ClO3, parentheses 2. This 2 is because of this +2. Okay? Now I think going from names to formulas is a little, formula to names easier, because K2SO4 is called, K is potassium. Whole name of the metal, K is potassium. K is potassium, sodium is Na. K is potassium, sodium is Na. Right? We just say that over and over. I've said that so many times today. SO4 is sulfate. So you just use sulfate. That's it. So I'm just saying the whole name of the metal and then the name of the polyatomic. Now this one, the polyatomic is out front. So that's called what? It's the ammonium. But then what do I have to do with the bromine? Yes. So what would I say? It's ammonium bromide. Because then it's acting like the non-metal of an ionic compound, which is like chloride, bromide, fluoride, nitride. BeOH2, that is beryllium and OH2. Not oxide.
I'm sorry, hydroxide.
Hydroxide. Right? So remember that OH, when you see the OH, is telling you that's the hydroxide. So I don't have to change it. It's just the hydroxide ion. And then the last one, Al2CO3. Looks super complicated and fancy, but it's just what? Aluminum, whole name of the metal, and carbonate. CO3 is a carbonate. So don't try to split those ones up. And here'll be another thing. If you see that it's an ionic compound and you see there's 3 elements, odds are there's a polyatomic in there. You got to figure out which one it is. All right. Why do we talk about ionic compounds? Well, ionic compounds are really important in functioning of the body. They really don't build structures. So your carbohydrates, your proteins, your nucleic acids, lipids, they're not made of ionic compounds. But ionic compounds, when you eat things like that contain sodium chlorides, you sprinkle table salt on your food, as soon as that hits your tongue, sodium chloride has the ability to separate into sodium ions and chloride ions. It dissolves in water. And so when they talk about your fluid and electrolytes, the electrolytes are these. Okay, so these are the electrolytes in the body. And electrolytes are really important. If they get out of whack, then you can have all kinds of problems that occur. Sodium. Sodium's really big job is it is your water balancer. And anybody that has had too much salt knows what happens. So if you go out and you have like the typical southern meal where you have barbecue with potatoes, with green beans, with some hush puppies, right? So you go out and you have the typical fare, the southern fare. There is salt in the pork. There is salt in the potatoes. There is salt in the green beans. There is salt in the hush puppies. That's why they're delicious, okay? But how do you end up feeling afterwards? What do you notice about your hands, feet, your rings? They're tight, right? Do you ever notice how like then you're like, gosh, my fingers, my ring's tight. That is because when you ingest a lot of salt, water goes with it. And so if you eat a lot of salt, that salt will get filtered out through the kidneys, but that takes time. That doesn't happen like instantly. So that is why you retain fluid, and that fluid then collects under the skin, and that's what makes everything somewhat puffy. They call it edema. So you can have short-term edema. That's the easy edema. When people have chronic circulatory problems, excess salt intake can lead to chronic edema, where they end up with swollen ankles, swollen hands, swollen abdomen, everything begins to swell, and it's because their circulatory system can't manage, the kidneys can't filter fast enough in order to keep that off. So people that have any kind of cardiovascular disease, one of the doctor's orders is you're going to have to cut out salt in your diet, okay? Because by ingesting more salt, you're holding more water, and that puts more pressure on your heart, because your heart's trying to then pump more volume. And that increases pressures, that increases stress, and increases all the heart disease issue. Now, potassium. Potassium is really important, and it's really an important ion inside of cells, but it's important in nerve impulses. And if your potassium levels get low, it can actually cause nerves to stimulate the muscles spastically. And this causes you to wake up in the middle of the night, and what do you have? A muscle cramp, right? So you like get a leg cramp in the middle of the night and you're like up staggering around the house. What does your mother tell you to do? Yeah, that works for me. But what's the food besides mustard and pickle juice? A banana. Yeah. So that used to always be what mom said, was like, if you have leg cramps, well, you should eat more bananas, because bananas are high in potassium. Okay. So this helps potassium really has a function in terms of nerves. But what it does is it can stimulate irregularly muscle contraction. So that can actually lead to leg cramps. Magnesium's another one, though, that sometimes is a culprit with this. Magnesium's another one that is typically found more inside of your cells than out, like potassium. But it also triggers nerve impulses. So if your magnesium or potassium get low, both of those can be side effects or causes of leg cramps. And I do not understand the mustard thing. It like totally works though. Like I am notoriously wake up. It's usually for me, it's if I don't drink enough water. If I'm a little dehydrated, then I will get muscle cramps in the middle of the night. Like literally the kind I get up and I'm just pacing all around the house, like trying to get it to stop. And what works for me is yellow mustard, which is really gross, like to just shake and like squirting your mouth in the middle of the night. But like within 30 seconds, the cramp eases off. It's very bizarre. I don't know if it's the vinegar. I don't know if it's like whatever that's in the mustard, but pickle juice does the same thing. I'm not a pickle juice fan, so I don't really, I mean, I'd rather eat a tablespoon of mustard, but then I got to go brush my teeth afterwards because I'm like it's like all I can do is taste mustard. But those are the really quick fixes for leg cramps. Other example of an important electrolyte, iron. So iron as a +3. So iron is ingested primarily from red meats, from liver, leafy vegetables. What it's used for though, remember, it's what is collected inside of red blood cells. It's what allows those red blood cells to carry oxygen. So if you don't have enough iron, then you end up with anemia. So these electrolytes, they're not used to build big things, but they're really important. So remember, most of these are all those minor elements and trace elements that you've got in the body. Ones down at the bottom, the anions, the negatively charged ions, we are neutral as a whole, right? Because when you ingest salt, you don't just ingest sodium, you ingest sodium chloride. So you end up ingesting both come in. So the chlorine or chloride ions are basically floating around in all the fluids, and they help to balance out all those positive cations that are in there. One that we will talk about is called the bicarbonate ion. It's HCO3. So it's like the carbonate, but it has a hydrogen on it and only a single negative charge. But the bicarbonate ion is very important in pH balancing. So when we talk about acids and bases, we're going to talk about acidosis, alkalosis, what happens when your blood pH gets out of whack. And the bicarbonate ion is one of those ions that plays a role in trying to make sure that doesn't happen, trying to make sure that everything stays balanced. Okay, so when I think of electrolytes, I think of ions, and I think of them as having a real important functions in the body. They don't really build big things, but they're really important in making sure certain things work. Nerve impulses, muscle contraction, blood clotting, bone strength, like all of those are all because of these electrolytes. When we think of building blocks, though, like the reason we're the size that we are, it's really because of these types of molecules, covalent molecules. So covalent molecules, they are made by this sharing. It is all nonmetals. So remember, where are the nonmetals on the periodic table? Metals are to the right of that zigzag line. Okay, so when we talk about nonmetals, we're really talking about carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, iodine. These are really the nonmetals, the ones over on this side. But I'm also going to throw in hydrogen, because hydrogen really acts more like a nonmetal. Like if you look, you see it's a gas, like most of the nonmetals are. It's got one valence electron, and all it needs is two to be stable. So it has a strong attraction for its electron. It doesn't give its electron up as easy, so it acts more like the nonmetals do. The way that these form a bond is there's no transfer of electrons. This happens because you have two atoms that need about the same number of electrons, and so they tend to share. So for example, if I have two chlorines, if I have one chlorine and you look at the periodic table, it's got 7 valence electrons. Remember, that would be 7 dots around. If I look at another chlorine comes along and it has 7, one chlorine cannot pull electrons from the other chlorine. So instead, if I have those unpaired electrons go between the two, so this chlorine has its 6 non-bonding electrons over here and its 1 here. The purple chlorine has its 6 belonging to it, and then it shares a purple electron with the red chlorine. Do you see that that fills the 8? So now this chlorine has its 8, this chlorine has its 8, and it's stable. So then it can behave as if it's a noble gas. You will see this drawn oftentimes with the dash. So just remember, the dash means it's a pair of electrons. 2 electrons is a dash. You should also include the electrons that belong exclusively to each chlorine. Those are those non-bonding electrons. They don't participate in the bond. A way to think about this is like what happens when you share custody, right? So you have mom and dad, they have a kid, split up, but they're sharing custody of this kid. So that's what those electrons are. The ones in the middle, they're shared. So they spend some time with one, some time with the other. So they go back and forth, but that allows the purple chlorine to act like it has 8 and the red chlorine to also act like it has 8 by doing this sharing. The only one that's the oddball is hydrogen. So hydrogen exists as H2, right? So it exists in nature, hydrogen gas. H2 is formed, hydrogen has 1, and when it comes up against or around another hydrogen, they share a pair, but how many electrons does hydrogen need to be stable? What did we say? Hydrogen only needs 2, right? Because 2 makes it like helium. Hydrogen has 1 electron, but 2 is going to make it stable. That's why helium's a noble gas with 2. And so that creates that stable, not octet, the stable pair for hydrogen. Hydrogen only ever forms a single bond. Same thing with fluorine, chlorine, bromine, and iodine. They're all in group 7, so they're only ever going to form a single bond to make 8. So they'll only ever have a single dash. So that makes things pretty easy to remember. Like, so fluorine, chlorine, bromine, and iodine, these have 7 electrons. They form 1 bond. Remember, that makes their 8. Hydrogen has 1 electron and also forms only 1 bond. So hydrogen will never have more than just a dash attached. Fluorine, chlorine, bromine, and iodine will never have more than just a single line attached. They'll never make a double bond. They'll never make a triple bond. The only ones that you have to look at a little closer to figure out how they come together is nitrogen, oxygen, carbon, and then sulfur and phosphorus. Okay? Those ones that are in group 4, 5, and 6, they are nonmetals. They're just nonmetals. So the carbon has 4 electrons. Transition metals are the ones that are from row 3 to 12. The capital B. Remember the nonmetals. These ones are nonmetals. So the ones down in that row with the B's, those are all transition metals. The only nonmetals are the ones to the right of the zigzag line. But carbon is in group 4A, so it has 4 valence electrons. So it's got to share 4 bonds in order to make 8. So always 4 bonds. Nitrogen has 5 valence electrons. It's in group 5. That means that it's going to need 3 bonds in order to be stable. And really, phosphorus is the same. Oxygen and sulfur, they have 6 valence electrons because they're in group 6. And in order to make 8, they have to have 2 bonds. So if you see a single dash, you remember that means it's a pair of electrons. So if I have 2 dashes, that's a double bond. That represents 2 pairs of electrons, or a total of 4. So this is a double bond. And remember that that's the equivalent of 4 electrons. Whereas a single bond means that's just 2 electrons. Okay, what about the nitrogen with the 3? That's a triple bond. So how many electrons does that represent? 6. So each line is 2. So if I have this triple line right here, that is a triple bond. And that is actually 6 electrons. Carla, what do you have a question?
So from group 4A to 6A,
Mm-hmm.
metals.
Non-metals. They're all non-metals. Look on their zigzag line. Everything to the right of the zigzag line is a non-metal. Okay? Everything to the left is a metal. Covalent molecules are always non-metals and hydrogen. Okay? So let's just do some for examples. Here's the first one. So this one is CH4. Okay? And we're going to do like the basic 5 because those basic 5 let us look at shape and even talk about polarity. So CH4 from the formula, 1 carbon, 4 hydrogens. Yes? That's the formula. So when you go to try and draw this, you always list your atoms, their number of electrons, and how many bonds you need. So I know that I have 1 carbon. It's right here. I have it listed. There's 1 carbon. Each carbon has 4 electrons. And so that means that I have to have 4 bonds, right? In order to make 8. 4 electrons means 4 bonds. 5 electrons would be 3 bonds. 6 electrons would be 2 bonds. So carbon has 4 bonds that I'm going to need. Hydrogen is the oddball in this because hydrogen has 1 electron and only forms 1 bond. So it's a 1 and 1. 2 makes it stable. So the next rule, when I go to draw this, I always start with the atom that needs the most bonds. So that means I got to start with carbon. So I put carbon down first and I put its electrons and spread them out. So carbon with 1, 2, 3, 4. Now I add the remaining hydrogens, creating a pair. The pair goes between the carbon and the hydrogen. So I'll add 1 hydrogen here and form a bond. That's 1 hydrogen. Then I add another hydrogen, form a bond. Then 1 more hydrogen, form a bond. And then I can add the last one. Notice that I'm pairing the carbon's electron with one of the hydrogen's electrons every time I form a bond. So it's like I have 1 purple and 1 red. And when I get done, can you see that carbon has 8 around it? And each hydrogen has 2. They call that the dot structure, electron dot structure. But you can also write it as the Lewis structure, where you just change any paired electrons become a dash. So here's like the long and drawn out steps. Okay, and we're going to do this one for water. So first, list the atoms in the formula. So in H2O, I know that I have 2 hydrogens and I have 1 oxygen, right? Okay, so I've listed them. Now I want to list the number of valence electrons and the number of bonds that each atom is going to need. So hydrogen has how many electrons? 1. 1 electron, and it needs 1 bond. That won't change. That's always the case. Oxygen has
8. No.
its atomic number is 8, but look at its group number.
6.
So 6 electrons. Remember that this is the group number. Right, and so I've got to make 8. So that tells me I know I'm going to end up having to link it to 2 bonds. So now, step 3, I'm going to put down the atom that needs the most bonds and put its valence electrons around it. So the one that needs the most bonds is, so I'm going to put oxygen, and I'm going to put it 6 dots. So when you go to put your 6 dots around, make sure 2 sides need to have 2 electrons and 2 sides need 1 electron each. That makes it 6. Don't put like 2, 2, and 2. Make sure that you spread them out. So see in my oxygen, I have 6 electrons, 2 sides, and I don't care what sides, but 2 sides need to have 2 dots. 2 sides should have a single dot. Now I'm at step 4. I'm going to add the next atom which needs the most bonds, pairing single electrons with the existing atom. So where do I want to put my hydrogens on here?
On this side.
On the,
Right?
okay, one on the right, and I'm pairing it. Okay, so by setting the red dot next to the blue one, now I'm creating a covalent bond. All right, I got 2 hydrogens, so where does the other one go? At the bottom. So now I'm going to put this hydrogen down here, and by putting the red dot next to the blue dot, that's another bond. Okay, and now I'm done. I've used my 2 hydrogens, I've used my oxygen, there's my water molecule. So that is called the electron dot structure. If I was going to do what they call the Lewis dot structure, I would just have dashes for each of the pairs of electrons that are shared, and you can include those non-bonding electrons because we're going to talk about the shape and those come into play. Okay? So these are sort of all the steps. I didn't even have to go to step 6. So let's try one that uses step 6. Step 6 says if I've put all my atoms down and I still don't have 8 for everything but hydrogen, that's when I have to make a double bond. Okay, so let's try that one. Well, we can't do it with any of those. Let's try that one. Let's try it with oxygen, O2. So if I have O2, oxygen, how many electrons does oxygen have? 6. So I have 6 electrons, and that means each one has to have 2 bonds. So they're exactly the same, so it doesn't matter which one you start with. So O, 1, 2, 3, 4, 5, 6. 6 dots around this one. Now I have to add the other oxygen. Where do you want to add the other oxygen? To the top, to the bottom, to the left, to the right? To the right. I've got to add it to one where there isn't a pair. So I'm going to have to put my other oxygen 1, 2, 3, 4, 5, 6. So the pair that's in between, and it wouldn't be wrong if I put the one underneath. I could put it there, or I could put it down here. That's fine. As long as those 2 dots are between the 2 oxygens, that represents a bond. But now I'm done, right? I've put down all my atoms. So I'm done now, but when you count, do you see that there's electrons that don't have pairs? So the one underneath each oxygen is single. They don't have pairs, so these have to move between. So they are going to move between the 2 oxygens, which will form a double bond. So this one will move, and this one will move. Purple one here. The red one here. Now when you count, do you see 4 in between? And then 4 belonging to each. So 4 and 4 makes their 8. You don't do this until after you've put all of your atoms down. Don't try to make double bonds or triple bonds. Start off, try to just link everything together with single. And if you can't, then you have to go to the double bond. And if you still can't get it right, then you have to go to a triple bond. But those are like the last steps. So I would draw this, an O, dash, dash, to an O with its dots. And that's how oxygen gas is found. It always exists as O2. So let's try CO2, carbon dioxide. So CO2, carbon has 4 electrons, oxygen 6 electrons, 6 electrons. Remember that's the group number. So carbon needs how many bonds? 4. Oxygen's 2. So always start with the atom that needs the most bonds. That like goes down first. So I'm going to put what down first? So I'm going to put carbon with its 1, 2, 3, 4. So now I have 2 oxygens I have to add. So I just got to add 1. So if I add 1, 1, 2, 3, 4, 5, 6. So now comes the question, do you see that carbon has some dots that aren't paired? Do you see that oxygen has a dot that's not paired? So this is where people go, well, how do you know where to put the other oxygen? So the rule with this is I always add to the atom that still needs the most bonds. So out of those two, the carbon and the oxygen, I have down which ones need the most bonds. The carbon. Can you see that carbon still needs 3? That tells me put the oxygen there. So it's not random where you set them. I want to put it on the carbon. I'm going to change just so that I have a different color. I'm going to put my oxygen over here. 1, 2, 3, 4, 5, 6. So now I'm done. I got all of my oxygens, all of my carbons, all of my electrons are down. But am I done? No. Can you see that there's a bunch of dots without pairs? Okay. And sometimes like making sure you draw your molecule big enough helps you see. Sometimes I see people like write it so small. I'm like, I don't even know where your dots are. Your dots are so little and everything's all squashed together. So like make sure you draw it like big enough so that you can make sure you know these dots are above and these dots are below. So, or use the colors because I think like the colors just help me see it as well, that they're paired or not. So I'm going to have to move electrons. I'm going to use, starting with the black oxygen and the red carbon. I'm going to move 1 red electron and 1 black electron, the ones from the bottom that are not paired. I'm going to move these. I'm going to move them so that they're between the 2 atoms they belong to. So like the red carbon's going to still stay next to the red carbon. The black oxygen electron will still stay next to the black oxygen. I'm moving these ones. So now I got a dot here. Oh, sorry. And I got a dot here. So when I look, do you see now that carbon, the red carbon and the black oxygen have 4 in between? And oxygen, the black oxygen has 4 of its own. So 4 and 4 makes it 8. So it's done. But the green oxygen is not done yet because the green oxygen has 7 and the carbon has 7. So I'm going to have to move the other electrons that are not paired. So this one and this one are going to end up being moved between the oxygen and the carbon. Moving this one, moving this one. Changing color. So the oxygen's dot is there. Nope, that's not black. There. Now when I go back and count, do you see 8? Can you see that the green oxygen has 8? 4 between and 4 of its own. The black oxygen has 4 between, 4 of its own. And carbon has 4 on either side. So they all have their 8. So that is stable. So when I draw the Lewis structure, or the electron, the Lewis structure, I just put every pair of dots is a line. Yep. So we did CH4, H2O, CO2. Everybody got this one? Try this one. This is like the 4th. There's 5. There's 5 basic like ones that we draw, that you'll draw in lab that we've used over and over. CH2O, its common name is formaldehyde. So formaldehyde is found in like preservative, like embalming fluid. So see it down there. So CH2O. So 1 carbon, hydrogen, hydrogen, oxygen. I just like listed them all individually. So I know that I have 4 electrons for carbon, 1 electron for hydrogen, 1 electron for hydrogen, 6 electrons for oxygen. So that means carbon needs how many bonds? 4, always. Hydrogen? 1. Oxygen? 2. The number of electrons plus the number of bonds is always 8, except for hydrogen, it's only ever 2. So which one do I start with? Carbon. C, 1, 2, 3, 4. Right? There's my 4 dots. Which do I want to add next? Why? It needs the most bonds. That's the reason. Okay? So if you have more than 2 different kinds of atoms in your formula, You always start with the one that needs the most bonds, then you add the one that needs the most bonds next. That's always what like controls that. So I know I've got to add oxygen next. 1, 2, making a pair. 3, 4, 5, 6. So my purple dots, I have one of them is paired. 2 pairs belong to oxygen. There's a single at the bottom. Now I got to add 2 hydrogens. Where do I add the hydrogens?
Can you add on one on that side and that side?
Okay, what's the rule? Which one do I need to add the hydrogen to? The one that needs more bonds. So which side still needs more bonds? All right, okay, so let's just add 1. So I'm going to add 1 hydrogen here and make a pair. I still have to add 1 hydrogen. So which one does carbon or oxygen, which one still doesn't have enough bonds? Carbon. Do you see that? That's how you know. So you don't randomly place them. You always put them onto the atom that you've already put down that needs the most bonds. So that's going to tell me to put my hydrogen above or below. Doesn't matter. Okay? So there's everything. I've used my carbon, 2 hydrogens, and my oxygen. And do you see the pair at the bottom that are not paired? Where do those go? In between carbon and oxygen. They cannot go between carbons and hydrogens because hydrogens never ends up with more than 2. So I can't make like a double bond between a carbon and a hydrogen. That never happens. So this is going to move here. This is going to move here. Okay, so I'm going to make a double bond there. So this one slides and this one slides. So I end up with moving that black carbon electron and moving the purple oxygen electron. That's a double bond. So I end up with a carbon double bonded to an oxygen and then a single bond to each of those hydrogens. Okay, those ones are really the 2 harder ones, CO2 and CH2O. Those ones you've got to put those double bonds in. So you do this one, NH3. That's the 5th one. So CH4, H2O, NH3, CO2, and CH2O. Those are pretty much those 5 basic ones. So just about everything that you see is just like that. Do NH3. Yeah, we did CO4 and we did H2O already. Those ones you could go back and fill in, but we did them on a previous slide. So how many electrons for nitrogen? 5, which means how many bonds? 3. And then the hydrogens, 1 and 1. So which did you start with? Nitrogen. And you got to make sure that you put your 5 dots. One side should have a pair. I don't care which one. I just always put it at the top. Okay? One side should have its own pair. The other 3 should be singles. And then, where did you add? Hydrogen here, hydrogen here, hydrogen here. Till I've added my 3. And can you see the 8? Nitrogen has its 8. Hydrogens have their 2. Okay? So that's the drawing. So all of the other ones that we use as examples and such are really nothing more than like examples of these. They're just, sometimes instead of a hydrogen, it might have a chlorine, or it might have a fluorine, or it might have a bromine. And so I could swap hydrogens out for those because they only ever form a single bond. So it would still be like if I had, instead of CH4, if I had CCl4, it would look exactly the same. Instead of H's, there would be Cl's because they just form single bonds. I'd still start with carbon, put it in the middle, and I'd end up adding a chlorine on either side, above, below, left, and right.
Would we ever have a triple one on the test?
There is an example of a triple one. I'm not going to ask you to draw them. I'm going to ask you to actually pick them out. Okay, so on your test, huh? So in this one, HCN actually is one with a triple bond. So that one, hydrogen has 1 electron, carbon 4 electrons, nitrogen's 5 electrons. So remember that's 3, 4, and 1 by number of bonds.
That's how we gotta put.
What would I start with in this one?
The nitrogen.
Nope, which one needs the most bonds? So that's another, that's like, sort of like people want to say that S is sodium. This is another one. People look at this and they think 5 electrons, I got to put that down first. No, you want to put the one that needs the most bonds. If carbon's in the list, it's always carbon. If it's not carbon, then maybe it's nitrogen. And if it's not nitrogen, maybe it's oxygen, because that goes down in order. So I got to put the carbon first. And then I've got to add what next? Nitrogen, because it needs 3 bonds. Hydrogen only needs 1. Hydrogen gets added last. So nitrogen would be the next one. 1, 2, 3, 4. And then the 5th one pairs. And now I've got to add hydrogen. And so what's the rule? Which side do I want to add that hydrogen to? Because the C is 1, 2, 3, and 1, 2. Do you see that carbon needs 3 bonds still? Nitrogen only needs 2. So I want to make sure that I add the hydrogen to the side that needs the most bonds still. So can you see why this ends up being a triple? I cannot add any more bonds between carbon and hydrogen. Carbon and hydrogen, when it gets 2, it's done. The only other place to add is to start taking the black carbon electrons and the red nitrogen electrons and pairing them. So I'm going to have to move this one and this one, and then I'm going to have to move this one and this one. So they're all going to end up between the carbon and the nitrogen. Oop, not that one. I'll put it back, hold on. That one's still there. But I end up with one here, and then one here, and one here. So those electrons that were above the carbon and below the carbon move between the carbon and the nitrogen. The electron that was below the nitrogen and to the right of the nitrogen move between the carbon and the nitrogen. That's a triple bond. So this would be an N with the 3 lines to a C, single line to an H. Okay? This is really not very common. You don't really see triple bonds. They're very reactive, so they tend not to be found in nature. Although nitrogen gas exists this way, but most of them don't. So the last thing to cover in this is how do you name these things? This is the easiest way to name them, okay? Naming covalent molecules where there's only 2 elements. Here's the challenge in life. When you see this, what do you call this? Carbon what? Carbon dioxide, right? CO2 is carbon dioxide. Okay, the reason we use this, do you notice you use the whole name of the first element? Just like ionic. You use the first part of the second element plus IDE. But I have this di. Di tells me that's 2 oxygens. I have to have a number prefix because carbon and oxygen can actually combine in a lot of different ways. I can have all of these. So it's not like NaCl. So remember NaCl? That's the only way I can write NaCl. I can't have alternate numbers of sodium and chlorine. All they are is that 1-to-1 ratio because sodium is positively charged, chloride is negatively charged, and that's how they combine. But with covalent, because they share, they can share differently. So I could have like a carbon sharing with an oxygen, sharing with an oxygen, sharing with another carbon. I can end up making lots of possible like balls and sticks attaching them. So because of this, they said, we're going to have to write how many of each atom is present. So we use these Greek number prefixes. So here they are. If you only have 1, and this is the second element only. If the second element has only 1 In the formula, you use the term mono. So one oxygen would be called monoxide. One nitrogen would be mononitride. One chlorine would be monochloride. Okay, if the second element only, if the first element is one, you just leave it off. That's why carbon dioxide, you just call it carbon. We don't use mono for the first element. All of these other ones, so di is 2. Tri, like a triangle, that's 3. This fourth one's a little weird for people. Tetra. Tetra means 4. And you know how I remembered this when I learned it? Did you ever play the little video game called Tetris? You always moved around little blocks of 4. So sometimes it was a little square, sometimes a straight line, sometimes an L. So it was little blocks of 4. So I always could remember, oh, well, Tetra is 4 because of that game. That was a long time ago too. All right, but then from there, they just start following geometry. So a pentagon is a side of 5. Hexagon has 6. Heptagon is 7. Octa would be 8. Nona is 9. And then deca is 10. And you don't see those very much, but just so that you know. Plus, we'll use them in the next chapter anyways. Okay? So I would say like those first 4 you kind of got to get used to. Mono, di, tri, and tetra. So for this one, if I have NO, just 1 nitrogen, 1 oxygen, I use the whole name of the first element, so that is called, N would be nitrogen. Now the second element, I have to indicate the number even if there's only 1, so this would be monoxide. And do you notice that they don't put double vowels together? So it's not monooxide, it's just monoxide. So if there's like 2 O's, if mono has an O and oxide has an O, you just drop one of them. Okay, but what do you think the next one would be? N2O. It's nitrogen, but there's 2 of them, so I have to say what? Yes. So I have dinitrogen, but then 1 O means monoxide. So what is NO2? Dioxide. So if nitrogen, if the first element's only a 1, you don't need the mono. But you always have a number prefix for the second. If there's just 1, it's a mana, whatever. N2O4. Well, you got 2 of them. 2 nitrogens is, and then 4 oxygens. And so here's a double vowel. They would call it tetroxide. So double vowels, you would just drop the A out of tetra, so it would just be tetroxide. I don't care. If you wrote tetroxide, I would not mark it wrong. But your book might, and mastering might. All right, and then you got CO2. Okay, so we did CO2. So what's CBr4? Carbon. Tetra. Tetra. And then what's the Br? Bromide. Yep. First part of the second element plus IDE. So do you see how the naming is kind of like ionic? Whole name of the first element, first part of the second element plus IDE. Just make sure that you add those number prefixes. So let's do this. Give the name or the formula. So this is on the back page of your little half sheet, worksheet thing that I gave you. Trinitrogen dioxide. What would that be? N3. O2. That's right. Trinitrogen, N3, dioxide, O2. How about tetrasulfur pentachloride? S4, Cl5. I think these ones are pretty simple. You don't have to assign charges. You don't got to swap. You don't got anything. Yeah, it's that. It's on that back page. Huh? You just have to remember to put the number prefixes. So dicarbon hexahydride. C2, H6, hexa. Hydride is hydrogen. So CF4. Carbon. Not in front. Mono, you don't have to use mono for the first element. No Roman numerals in covalent. That's why I said this is it. There's no exceptions. Okay? There's no exceptions to this. You use the whole name of the first element, first part of the second element plus IDE, then add those number prefixes. Okay? Exactly. And remember, fluoride is UOR, otherwise it's flour. So what's SO? So. Not sulfur oxide, sulfur. Monoxide. Right? So remember, if the second element is 1, put mono. If the first element's 1, you don't gotta. P2I4. Diphosphorus. Tetraiodide. I would drop the A out. I'd say tetraiodide. But that still even looks weird, doesn't it? Okay, so here, these are actually supposed to be blanks. I don't know what happened. Do you have blanks on yours? Good. So for the first one, iron 3 sulfide. You tell me, is that ionic or covalent?
Covalent.
How do you know?
Because of the 3.
Nope.
I'm just guessing.
Okay. Think. Ionic or covalent, how are they different?
I just did this. Ionic is
Look at the first element. So here's how you tell this. Look at the first element. So whether it's in the name or if it's in the formula, look at the first element. If the first element is a metal, then you know it's what? Ionic.
and iron is
Iron's a metal, so this is ionic. If it's a non-metal or hydrogen, then you know it is covalent. So what's the second one? CaNO3 2. Ionic. Because of the calcium. Calcium's to the left of the zigzag line. What about S4O2? Covalent, because that's sulfur. What about potassium nitride? Ionic. Find potassium, remember that that's K. Then PBr3. Covalent, phosphorus. Pentanitrogen trihydride. Huh? It is. Nitrogen is what? Covalent, because it's a nonmetal, right? So it's on the right of the zigzag line. So if the first element's to the right of the zigzag line, it's covalent. If it's to the left of the zigzag line, it's ionic. Cu3P. Ionic. And this last one is really mean. I put this one in here just so that it's sort of like your only exception, ammonium. What is ammonium phosphate? It is a what? That's ammonia, but ammonium is a polyatomic ion, so this would be, if it's an ion, it has a charge. So if it has a charge, this molecule would have to be ionic. Okay? So the thing you have to remember here is this is NH4 with the plus. So if it's an NH4 with the plus, that's the only time nitrogen out front is an ionic compound because it exists as an ion. That's a polyatomic. So now that you know which ones are ionic and which ones are covalent, when you go to name the ionic, like for the first one, iron 3 sulfide, what do you have to do in order to write its formula? What do I have to do? Right? So first I got to write down the what? Fe. And the charge is +3, right? Remember that the Roman numeral tells you the charge. So I know, so this part tells me that it's Fe with the +3 or 3+, doesn't make a difference. Sulfide, what's that? Sulfur, so that's a what? An S, and the charge is -2, good, yeah, right? Remember, it's 8 minus the group number. It's in group 6, so I just think of it, it's got to gain 2 negative electrons to make 8. So that's why, since it gains negative electrons, that second element is always going to be negative. So now I've got this. How do I figure out the formula? Swap them. How many irons do I have? Fe2, S3. So the charge on the iron tells me how many sulfurs. The charge on the sulfur tells me how many iron. What about the next one? I think naming this one's not too bad. Ca, parentheses, NO3, 2. Calcium. What's that NO3? Yes. Calcium. Whole name of the metal. And then NO3, you've got to recognize when you see a bunch of oxygens, it's going to end up being a polyatomic. That is the nitrate. Right? NO3 is a nitrate ion. All right, so last one, then I want to stop because we have to go upstairs. And we're actually doing this today. So you guys should like fly through this in lab. So S4O2, covalent. So how do I name this? It is a sulfur oxide, but what do I got to add? So it is not sulfate. Whole name of the first element. So it's just tetra sulfur. First part for the second element plus that IDE. So what would that be? Dioxide. Just make sure you remember covalent, whole name of the first element, first part of the second element plus IDE. So that follows the regular ionic naming. Just go back, make sure that you add the number prefixes. Covalent need number prefixes. So I'm going to leave those 1, 2, 3, 4, 5. So there's 5 for you to practice. We will do these ones next time, and then we're going to talk about geometry, polarity, moles and molecules, and we're done chapter 3. All right.